Welcome, everyone. Today, we are going to dive into an architectural blueprint for evaluating advanced RAG paradigms. Specifically, we'll be discussing exactly when and how you should deploy GraphRAG and Agentic RAG in your production systems, all based on a rigorous empirical evaluation across 9 different semi-structured data scenarios. Let's jump right in. First, let's talk about the semi-structured data challenge. Basic RAG is fantastic when you're dealing with unstructured text, like pulling a single highlighted block from a stack of documents. But complex data is a different beast. Take the S*RK prime benchmark, for example, which features over 129,000 entities and 8.1 million knowledge graph relations. Real-world queries, like asking for a specific gene involved in vesicle transport that participates in a specific pathway, demand multi-hop reasoning over these explicit relations. To solve this, we looked at 3 distinct paradigms of augmented generation. First is regular RAG, which uses vector similarity search to retrieve text documents. Second is GraphRAG, which uses LLM entity extraction to drive subgraph traversals and retrieve data triplets. And third is Agentic RAG, where autonomous agents utilize specialized tools and iterative reasoning loops to find the answer. However, upgrading your system isn't without risks. Enter the complexity trap, or what we call token hemorrhage. Adding agents and graphs can increase your token overhead exponentially. This happens because of redundant graph structures and the need to inject full session histories into every single LLM call, which can easily cause frustrating context window overflow errors. So, how do we fairly evaluate these paradigms? We built a framework testing 9 standardized architectures against real-world constraints, highly restricted data access, critical latency targets of under 500 milliseconds, and expert domain knowledge. Crucially, we moved away from the standard raw retrieval ranking approach. Instead, we used an active end-to-end LLM generation evaluation to see what exact entity IDs the LLM actually selects in its final answer. Here is our 9 scenario comparison matrix mapping the complexity and integration levels. It ranges from text only in the regular RAG paradigm, moves through computed and predefined graphs for GraphRAG, and scales all the way up to fully autonomous agents with graph tools in the Agentic RAG category. Let's look at the results, starting with regular RAG. We discovered the massive power of one-hop injection. By applying a simple data engineering trick, appending neighbor nodes grouped by relation type directly into the entity documents, we achieved a hit at one score of 0.6972. This means simple text formatting actually outperformed sophisticated hybrid GraphRAG systems, and it did so with 0 added architectural complexity. This is incredible semantic value. When we evaluated GraphRAG, the core insight was clear: semantic context is mandatory. A pure graph search without accompanying text context largely fails, landing a low score of 0.1376. Even LLM-computed graphs degrade performance compared to curated ones. But, when you use a hybrid predefined graph that includes that vital text context, it becomes a very strong performer. Moving to Agentic RAG, we found an autonomy premium. Scenario 8, which used an autonomous agent with minimal tools, achieved the highest overall hit at one score in its category at 0.6881. Why? Because internalizing the query reformulation within the LLM's own reasoning loop maximizes contextual understanding better than using rigid, discrete tools. A quick warning though, adding explicit graph tools to agents actually degraded performance due to context bloat. Speaking of bloat, how do we optimize this? Let's talk about context optimization flow for graphs. The problem is that repeating entities for every single relation wastes space. The solution is a relation-grouped graph representation. Instead of listing entity A to be multiple times, we group the relations together. This simple fix reduces token usage from O(n) down to a constant O(1) for connected entities. For agentic RAG, the fix is the batch strategy. Standard sequential loops resend the full session history every round trip, which can easily eat up 250,000 tokens in just 5 calls. By using a batched approach, formulating multiple complementary subqueries and executing them in a single tool call, we reduced LLM round trips from 4.2 to 1.8, while actually increasing retrieval coverage to 94.4%. These optimizations pay massive dividends. We saw a maximum reduction in token usage of 53%. For instance, agentic RAG dropped from 466K tokens down to 244K. This freed up massive token budgets, allowing us to retrieve even more entities. But the big caveat is, did generation quality actually improve? The answer reveals a retrieval-generation gap, which acts like a leaky funnel. Even when we achieved an 83.5% ground truth retrieval coverage, the actual LLM answer extraction was only 47.9%. The paradox here is that retrieving more valid information is insufficient if the LLM cannot utilize it. Standard retrieval metrics are heavily overstating the benefits of advanced RAG. We identified a few drivers for this leaky funnel. Driver 1 is positional attention decay. The LLM extracts entities in the top 10% of the token context window with 97.9% accuracy. But beyond rank 50, extraction plummets to exactly 0%. It literally doesn't matter how relevant the data is if it's placed too low in the context window. Drivers 2 and 3 are semantic salience and the cardinality effect. Semantic salience means that LLMs inherently prefer canonical, well-known terms and will often ignore highly specific subtypes. And query-induced cardinality means that if your query uses singular phrasing, like asking for **an investigational drug, the LLM restricts itself and outputs only one entity, ignoring dozens of other highly relevant entities sitting right in its high attention zone. To bring this all together, we've built the RAG architectural decision tree. Do you have relational data? If no, use basic RAG. If yes, check your latency and cost budget. If your budget is strict, use regular RAG with one-hop relational injection for the highest ROI. If your budget is flexible, check if you have a curated domain graph. If not, go with autonomous agentic RAG with minimal tools. If you do have a curated graph, use hybrid GraphRAG with strict context optimization. To wrap up, keep these 3 production engineering principles in mind. Number 1. Optimize context before architecture. Group relations and deduplicate before adopting complex pipelines. Number 2. Measure generation, not retrieval. End-to-end extraction is what really matters. And number 3. Beware the context funnel. Remember that position, salience, and grammar dictate what your LLM actually uses. Thank you for your time, and good luck optimizing your production RAG systems.